let me start. And yeah, thank you very much to the organizers for kind invitation to this very exciting online event. And also, I happen to be in Hongo campus of University of Tokyo, and Katsura-san arranged a classroom, and there are maybe 11, 12 people present, so maybe you can add extra 10 or something to the number of participants. And yeah, following Tazaki-san talk, yeah, I'm going to talk about basically the same problem, but maybe from the slightly different angle. And my talk is also dedicated to the memory of Ian Affleck. And if you are not familiar with this background of my slide, so this is a photo of Vancouver, where Ian Affleck spent much of his life. And also I was very lucky to be his postdoc at Vancouver for a few years back in 90s. Okay. So yeah, so this is my photo with Ian. And Ian liked cycling, windsurfing, hiking, and he took us to many hikes. And so he was maybe 15, 16 years older than me, but he was very fit. So I was always struggling just to follow him in the hike. So it's still unbelievable to some extent to me that he left us so early. But he left many great physics and great memories. And actually, I'm trying to write up my memories of Ian. And this, so this is a Google document. So if you are interested, you can check. And yeah, it's still work in progress, but I hope to complete in sometime in the future. So, okay, so yeah, already Tazaki-san gave a very nice overview of the Holden gap phase and SPT phase, but just to remind you the main point, and also, yeah, sorry, I'm using somewhat different parameterization because this is more common in quantum magnetism field. So here I'm using D, but this D is related to Tazaki-san's small s in this way. This is just 1 minus s over s is D. Because in magnetism, many quantum spin chains are approximately Heisenberg chain, like a first term, like this. But often real magnets, spin 1 magnets are not completely isotropic, so they have some anisotropy. And this type of anisotropy is called uniaxial anisotropy, which is actually often present in real spin 1 material, especially many experimental material example of spin 1 system is based on nickel ion, nickel 2 plus, which carries spin 1. But then they often have this uniaxial anisotropy SZ squared. Okay. Then, because of the parameterization, the left-hand side and the right-hand side are swapped. Sorry about that. But in this parameterization, if you go to D infinity, then the ground state just corresponds. Ground state is just given by a trivial product state of S equals to 0. So this is the same trivial state as Tazaki-san discussed. And if you go to D equals 0, this is the ground state of Heisenberg chain. So as Tazaki-san mentioned, this is not yet completely rigorously proven, but because of the many numerical and experimental, many evidences, we believe that at D equals 0, we have a gap, and so this Holden gap, nothing but the gap predicted by Holden. And both sides have no conventional order, no spontaneous symmetry breaking, at least in the conventional sense. So they both look like a disordered phase naively, but as Tazaki-san emphasized, so there is actually quantum phase transition at finite value of D. And the question was where there is a transition. And the modern understanding is that the left-hand side, Holden gap phase, is so-called symmetry-protected topological phase, which is non-trivial, and the right-hand side is more trivial gap phase. And so SPT phase is one particular type of topological phases. So let me quickly review the history of topological phases. Of course, it's far from complete. But I think, at least in quantum physics, quantum many-body physics, these topological phases started with the discovery of integer quantum Hall effect, first experimentally in 1980. Then quickly after that, several important theoretical papers appeared. In particular, this TKNN paper, which identified under certain conditions the quantized Hall conductivity with Chan number with topological invariant quantized to integer. And then soon after that, experimentally, people also found the fractional quantum Hall states, which is even more interesting. Then Ruffling wave function appeared. In terms of field theory, it's described by Chan-Simon field theory, kind of topological quantum field theory. Then, of course, there was a lot of activities in quantum Hall effects. But then in 2005, these topological phases were extended to materials at zero magnetic field, most notably topological insulators. First theoretically identified by Ken and Miri. And basically topological insulators is some kind of insulators which can be described by free electrons. So which looks like just an insulator, but non-trivial one with edge state and so on, edge state or surface state. And this SPT phase is basically the generalization of these topological insulators, initially conceived for just for free electrons to more general interacting quantum many-body systems. And firstly, this was identified by Gu and Ben, followed by our papers. So in this sense, history of SPT phase started in 2009. But as Tazaki-san already discussed, actually, in some sense, the history started even earlier because there was the Holden conjecture in 81. And then AKUT state was constructed. Then people identified Holden gap phase. And this Holden gap phase turned out to be archetypal example of SPT phase. And yeah, already Tazaki-san mentioned, but in this paper, Denise and Romeus proposed that this string order parameter can characterize this spin one Holden gap phase. And then people verified that prediction numerically. So there are several papers, but here I'm showing one such paper which confirmed this picture. String order parameter can characterize the Holden gap phase. So this is a paper by Garbin and Arvas, published in 89. So there are two plots. So they just studied spin one chain by exact diagonalization. So the system size is not too big, 14 sides or something. But already you can see the difference between the usual spin-spin correlation function, which looks like a decaying, and the string correlation, which looks like saturating at some non-zero constant, even at a large distance. Of course, this is not proof, but strongly suggests that the string order parameter is non-zero in standard Heisenberg chain. And I'm showing this paper because title and conclusions are rather interesting because they call it hidden topological order by analogy to quantum Hall effect. So they did, know that this Holden gap phase is some sort of topological phase. But the problem was that I have to say that there is no clear definition of this hidden topological order or whatever at that time. But they knew that there must be something non-trivial or topological in it. So as I briefly reviewed and also discussed by Tazaki-san, so by around 1990s, many things about the Holden gap phase were known. So we knew that the Holden gap phase is some kind of non-trivial phase, although without any conventional sense of order. So this is some sort of topological phase. And indeed, there are a few non-trivial characteristics of Holden gap phase was found. One is the string order parameter, and the other is the edge state. And as briefly introduced by Tasaki-san, these two apparently different properties were explained as consequences of hidden Z2 cross Z2 symmetry breaking by Kennedy and Tasaki in 92. So actually, we knew pretty much about Horden gap phase even back then. So let me still review some more details about this Kennedy-Tasaki transformation. So Tasaki-san already discussed this edge state and hidden antiferromagnetic order, which you can easily see in spin 1 AKT chain. And this hidden antiferromagnetic order can be detected by this non-local string order parameter. And these can be exactly shown for AKT model, but expectation is that this non-local string order parameter is non-zero also in the ground state of the regular Heisenberg chain. And also this edge state, we expect to survive in the ground state of the regular Heisenberg chain. Although there is no proof, but people check this numerically, and numerically seems to be correct. Then, so as I said, both of these properties can be understood as consequences of this hidden Z2 cross Z2 symmetry breaking. And I want to explain again how very briefly. So this is a Kennedy-Tasaki transformation.
That's
yes.
it.
Is there any question? Or... Anyway, let me continue. So this is a Kennedy-Tasaki transformation. So this is a product of this exponential for all combination of J and K, where J is to the left of K. So this is highly non-local. And if you transform, for example, SZ operator at site J by this Kennedy-Tasaki transformation, you have this operator that is same SZ operator, but accompanied by this string operator extended to the left of this site J. And similarly, if you transform SX, you also obtain the SX, but then string is now extended to the right to the site J. So if you transform spin operator, you get something non-local, which is not surprising because this transformation itself is highly non-local. But then if you transform something and get non-local, then usually, we don't want anything non-local because we don't know what's going to happen for non-local system. But why this Kennedy-Tasaki transformation is useful is that if you consider regular Hamiltonian, like a AKT or Heisenberg, or even with this uniaxial anisotropy, and then apply this Kennedy-Tasaki transformation, then transformed Hamiltonian H tilde looks like this. This is already shown by Tasaki-san. But my point is that each spin operator acquires a very non-local string extending to the right or left, which is infinitely long. But because this Hamiltonian contains Sx, Sx, Sy, Sy, Sg, Sg, so if you consider Sg, Sg, for example, then both Sg has string extended to the left. Then for the infinitely long section, there is an overlapping string, which corresponds to exponential of 2 pi I times Sc, which is 1. So actually, if you have two overlapping strings, that vanishes. So as a result, you in the Sg term, you only have a single length of string between these two sides. So similarly, similar thing happens for Sx, Sx, and Sy, Sy. So as a result, the transform Hamiltonian is still local or short range interaction Hamiltonian because most of the string cancel with each other. And this Hamiltonian looks strange, not a realistic Hamiltonian, but still short range interaction. So that's why this Kennedy-Tasaki transformation is useful. And this Hamiltonian looks strange, but if you start from Heisenberg chain, which has SU2 symmetry, but the transformed Hamiltonian no longer has at least explicit or apparent SU2 symmetry. But this Hamiltonian still has the discrete global symmetry, that is invariance and the global rotation spins, pi rotation about x, y, and z axis. So such a symmetry is often called dihedral group, D2, which is actually equivalent to Z2 cross Z2. So because you have x, y, z axis, you might think this is Z2 cross Z2 cross Z2. But because, for example, pi rotation about z axis can be written as a product of pi rotation about x and y axis. So actually it's equivalent to Z2 cross Z2. So the basic argument with this Kennedy-Tasaki transformation is as follows. So you now mapped original Hamiltonian H to this dual Hamiltonian H tilde, which has this discrete Z2 cross Z2 global symmetry. And at least for some model, this dual Hamiltonian can exhibit spontaneous symmetry breaking of this Z2 cross Z2 symmetry. So let's suppose that this Z2 cross Z2 symmetry is spontaneously broken. Then that means that you have a long range order. This is very standard stuff. You are familiar with this in Ising model and so on. So if you have a long range order, you can detect by usual spin-spin correlation function. So in the dual system, because this symmetry is spontaneously broken by assumption, this spin-spin correlation function should go to some non-zero value when two spin operators apart at infinite distance. So this is a standard stuff. But now you can transform back to original system. So you transform this spin-spin correlation function by Kennedy-Tasaki transformation back to the original system. Then, as I said, that each SZ acquires a string extending to the left, but the overlapping part cancels. So what you are left with is this correlation function. So SZ, and a string in between. And this is nothing but a string correlation function introduced by Denise and Gomez. And because in the dual system, I assume that there is a long range order, then that implies that in the original system, this string order must be non-zero. So this means that if you assume that in the dual system, Z2 cross Z2 symmetry is spontaneously broken in very standard manner, then in the original system, the string correlation function must be non-vanishing. So there must be string. So that implies that this strange, string order parameter, mysterious string order parameter can be understood as a consequence of the usual spontaneous symmetry breaking in the dual system. And likewise, again, let's assume that this Z2 cross Z2 symmetry in the dual system is spontaneously broken, fully broken. Then, because the symmetry is Z2 cross Z2, the dual system must have a fourfold degenerate ground state. Like in, again in Ising case, the Ising has Z2, so if the symmetry is broken, then you must have a doubly degenerate ground state. So in this case, I have Z2 cross Z2, so the ground state must be fourfold degenerate. And again, you can transform back to the original system. And because this Kennedy-Tasaki transformation is unitary, all the energy eigenvalues should be preserved, spectrum should be preserved. So the original system must also have a fourfold ground state energy. But usually for AKLT or Heisenberg chain, when we have a gap, we expect just a single ground state, unique ground state. So it seems to be contradiction, but it's not really, because usually we discuss a periodic boundary condition system, then the ground state is unique. But this Kennedy-Tasaki transformation was defined for open boundary condition, at least in 90s way, because you need ordering of the sites. So you need a product of explanation for J smaller than K. So we are assuming the open boundary condition. So the conclusion is that so your original Hamiltonian has unique ground state for periodic boundary condition, but once you impose an open boundary condition, the ground state must be 4-4 degenerate if the Z2 cross Z2 symmetry in the dual Hamiltonian is spontaneously broken. And such ground state degeneracy, which occurs only for open boundary condition, can be associated with the existence of H state. So in this way, the existence of H state and this mysterious string order parameter, both can be understood as consequences of the spontaneous symmetry breaking in the dual Hamiltonian. Okay, so that's a story. So by the way, so this is the title of Tasaki-san's talk in part 1. So some cool title, you know. And I don't know how many people realize that there is an original reference to this title. Maybe not young people, but at least I remembered, and maybe some people in my generation remembers, because I think the original reference is this. So so this is Tasaki-san's lecture in 35th Condensed Matter Physics Summer School in Japanese Bussei Wakate Natsu no Gakko, which is still continuing every year, right? And so this was his lecture in 1990, okay? And this is the title of his talk. So kind of similar, but there is some difference. So now we have these SPT phases. So this, you know, shows our progress in physics over the last 35 years, I guess. Anyway, so this, if you are interested, you can Google and download a PDF file of this lecture note. Very, very nice lecture note, although in Japanese. So, but Japanese speakers can appreciate this lecture note. And so this was published in Bussei Kenkyu 1992, but the actual lecture occurred in 1990. And I think I was extremely lucky because in those days, usually only the first year grad student went to this summer school. Maybe nowadays more variety of people go to this summer school, but in my time, maybe 90% of participants were the first year grad student. And I happened to be a first year grad student in 1990. So without knowing anything, I just went there because it looked like a custom for first year grad student. Then Harutasaki came and gave this lecture. So I was kind of hooked into this subject, and that's how I started working on this business. And then I talked to Harutasaki, and then later, I think in the fall of the same year, October, November 1990, I visited him at the GAKSHUIN. And at that time, archive, the ePrint server didn't even exist. The archive started in 91, and the condensed matter section started in 92. So those were days before archive. So it was very difficult to obtain the most recent papers. And but I visited him in GAKSHUIN, and he gave me a copy of draft of Kennedy-Tasaki paper. And then I studied this and played around, and then I found this compact expression of Kennedy-Tasaki transformation. Although in the original paper, this transformation was given in terms of SZ basis. It's a bit complicated, but eventually I found this very compact representation of the Kennedy-Tasaki transformation. And basically this became my first scientific paper. So this was very important for me. And one advantage of this operator expression is that although original transformation was defined only for spin 1, by writing the transformation in this way, I could immediately apply this transformation to any integer spin chain. Somehow it doesn't work for half-ordered integer, but it works for integers. Then almost everything seems to be, similar things can be said for any integer spin. That is, you can transform Hamiltonian to dual Hamiltonian. Then dual Hamiltonian has Z2 cross Z2 symmetry and so on and so on. But what was interesting was that I could calculate this string order parameter for AKT state with arbitrary integer spin. Then what I found was that this string order parameter is non-zero if spin quantum number is in odd integer, like a 1, 3, 5. But the string order parameter vanishes for even integer, like a 2, 4, 6. So at that time, I was very puzzled because even for even integer spin, like a 2, 4, 6, AKT state looked like a very non-trivial. So I thought there must be some sort of non-trivial state or topological state. But this string order parameter vanishes. So I was thinking like maybe there are higher hidden symmetry which we didn't uncover yet or something. So I was trying to find some higher hidden symmetry or something, but I was not successful. And in retrospect, it was all natural because after 2009, we realized that indeed this indicated that spin 1 chain is non-trivial SPT, and also spin odd Heyden gap phase, spin 1, 3, 5, 7 are non-trivial SPTs. But if you have even spin 2, 4, 6, then Heyden gap phase actually is essentially trivial. That's what we found after 2009. But so in 92, I caught some evidence of this, but at that time, I didn't know what was going on. Okay, so yeah, as I explained, so we knew many properties of SPTs, at least Heyden gap phase by 1990s, 92 or 93 or something like that. But we didn't quite reach the concept of SPT until 2009. And interestingly, there is a 70 years gap, even counting from this Kennedy-Tasaki. And even before Kennedy-Tasaki, there are many findings like a string order parameter, H state, and so on. But even after Kennedy-Tasaki, there is a 70 years gap until it's 2009. So we were missing something very crucial. So the question was, what we were missing in 1990s? And my answer is very simple. So in 1990s, somehow we didn't ask very simple but crucial question. And that question is, under what condition the Heyden gap phase is distinct from the trivial phase? That's a crucial question. So we knew that it's somehow distinct from trivial phase, but we didn't really discuss what is the condition for the Heyden gap phase to be distinct from the trivial phase. So that was the status before 2009. But for me personally, this realization came in summer of 2009. So as I said, topological insulator was discovered in 2005. So by the time 2009, it became a very hot subject. So it was like everybody was talking about the topological insulators. So I attended many talks about the topological insulators. So in summer of 2009, I attended one of those topological insulator talks. And I don't remember who was giving the talk, but somebody working on topological insulator. Then he reminded us of a very simple argument why topological insulator is topological, kind of heuristic argument. So that is of course, real topological insulators are much more complicated, but you can start from very artificial construction. That is, we consider this bilayer system. And each layer is just an integer quantum Hall state. But the one layer has upspin electrons with Chern number +1. And the other layer has only downspin electron with a Chern number -1. So each layer is, integer quantum Hall state, but with a different opposite sign of quantized Hall conductivity, which means that each layer has edge state, but one layer has edge current going in this direction, then the other layer has edge current flowing to the opposite direction. So this is so-called helical edge state. So you can draw the dispersion relation like this. Upspin and downspin electron has opposite slope. So this is a helical edge state. And of course, you can say that, okay, so this is very artificial system, nothing to do with a real topological insulator. So because in real topological insulator, downspin and upspin electrons can be transformed with each other and so on. So in this artificial double layer, bilayer construction, upspin electrons and downspin electrons are completely decoupled, but it's not the case in the real topological insulator. But you can start from this artificial bilayer system and introduce some, coupling between two layers within free fermions. And you need to keep the time reversal because topological insulator, at least the most simplest class, is protected by time reversal symmetry. So if you break the time reversal, then topological insulator is gone. So you want to preserve the time reversal. So what I want to do is to introduce some coupling between these two layers, preserving the time reversal. Then we can show that as long as you keep the time reversal invariance, you cannot kill this helical edge state because there is a crossing point and there is a degeneracy. And I don't discuss much detail, but this degeneracy can be related to the Kramers degeneracy and the time reversal. So as long as you keep the time reversal symmetry, you cannot kill the crossing, which means that you cannot kill the helical edge. In this way, you can say that the helical edge state is protected by time reversal via Kramers theorem, even if you couple these two layers. Then you can identify topological insulator with some bilayer system coupled with some interaction, but still keeping the time reversal. So yeah, I attended many of such talks, but then suddenly I realized that okay, we can apply similar argument to the spin chain, which is even simpler, because as we discussed, in one chain and open bounding condition, then we have the edge spin, and this edge spin has spin 1/2. And if you have free spin 1/2, of course you have Kramers degeneracy if you keep the time reversal, which means that this edge state must be robust. You cannot easily kill this edge state as long as you keep the time reversal. So that shows that this Holden gap phase is a robust phase as long as you keep the time reversal symmetry, and as long as you keep the time reversal symmetry, you can kill this edge state only when you cross the quantum phase transition that we are. So basically, this shows the spin 1 Holden gap phase is SPT phase protected by time reversal, although I didn't know the word SPT phase at that time. So I was kind of excited, and I was doing some calculation and was thinking of writing the paper. But then I went to some workshop in Max Planck Institute in Dresden, and I met Frank Pohlmann, and we found out that we were working on basically very similar or almost the same problem, which was SPT. And he knew this Guen paper, which appeared maybe half year earlier in 2009 March. So he told me about this paper. So I was a bit disappointed, but still, yeah, we had some result to make into the paper. So eventually we agreed to write the paper together. That's how this paper appeared. And interestingly, so at that time, we wrote two papers on SPT, one about mostly heuristic understanding of SPT, including this Cramer's theorem protection of the edge state, and another paper on more mathematical formulation based on MPS. And so this paper, heuristic paper, we put on the archive first. But the interesting thing is that we also sent this paper to PRL, then rejected. So we just left this paper for a few years on archive, but eventually this was published in PRB. And it's kind of funny because after this, I cannot count how many papers on SPT phase appeared in PRL. And I would say this paper was more important than most of those papers, but the point is that if you propose something new, then quite often referees cannot appreciate. So you may get rejected. So maybe my message to young people is that if you get your paper rejected by PRN, HR, or whatever, then maybe it means that you propose something very new and they cannot understand. So yeah, don't be too disappointed. Anyway, so that was the story. And so this is another paper which we put on archive in October 2009. So this paper is more mathematical. So we use a matrix product state, and within matrix product state, we show that spin one coding gap phase is really SPT protected by one of those symmetries, as Tazaki-san explained. So yeah, but in this talk, I'm not going to discuss this mathematical formulation, but I just explained how to understand the protection by time reversal in heuristic manner. That's a Cramer's theorem applied to edge state. So I will briefly discuss the heuristic arguments for the other two symmetries, that is bond-centered spatial inversion and this global Z2 cross Z2. So first about the bond-centered inversion. So again, so these heuristics I found only after learning about this MPS mathematical argument. But once you know the result, it's kind of easy to find a heuristic argument. That is, so bond-centered inversion means that you draw this orange line and consider the inversion about this orange line. And then you are flipping these singlets, so spin one half singlet. And actually, you are also flipping this singlet and this singlet and singlet, which goes to the opposite side. But because there is always pair of singlet, so this singlet is paired with this singlet, and you flip both, so their sign cancels. But there is a singlet bond on the at the center, which you must flip. And if you flip the singlet, by definition of this singlet state, up, down, minus, down, up, if you flip, then you get a minus sign. So basically, this AKT spin one state is parity odd under this bond center inversion. Of course, there is subtleties because if you have 6 sides and impose a periodic boundary condition, then if you apply the bond-centered inversion, then you are flipping at least two singlet pairs here. So then minus sign cancels with each other. So this 6-membered ring AKT state is actually parity even. But if you consider this 5-membered ring, then this the symmetry line goes through one side and one bond. So if you apply special inversion, then you are flipping single bond. So this state is actually parity odd if you consider AKT. And the trivial product state, like a large state, is always parity even, because you don't get any sign. So that means that as long as you keep this bond-centered inversion symmetry, this AKT state belongs to parity odd, and the trivial state belongs to parity even. So they are always distinct. So in this way, we can see that this AKT state belongs to SPT phase protected by bond-centered inversion symmetry. Of course, there are a lot of subtleties. So actually, this MPS formulation is kind of more rigorous, although not completely rigorous, but a more rigorous way to define this parity of the state and the bond-centered inversion. And finally, this Z2 cross Z2 symmetry. So actually, the fact that the spin 1 Holden gap state is protected, the SPT phase protected by global Z2 cross Z2 symmetry could be seen from the Kennedy-Tasaki transformation, which was invented in 1992. But we have been missing this simple argument for 70 years or something. So the argument is as follows. So as I emphasized, so Kennedy-Tasaki transformation is non-local. But Kennedy-Tasaki transformation is useful because the Hamiltonian is transformed to dual Hamiltonian, which has only short-range interaction. So this argument is only useful if the dual Hamiltonian is short-range interacting and has this Z2 cross Z2 symmetry. So we should ask under what conditions the dual Hamiltonian is local. And indeed, if you look at this transformation, we can easily see that the condition is exactly that the original Hamiltonian has the same symmetry, Z2 cross Z2. Then the dual Hamiltonian has short-range interaction. That's basically because if you have Z2 cross Z2 symmetry, SX operator cannot appear in Hamiltonian by itself. It must be always accompanied by another SX. SZ must be accompanied by another SZ. Then string operator, string parts should cancel with each other. Then you end up with short-range interaction Hamiltonian. So the condition was really simple. So if the original Hamiltonian has global Z2 cross Z2 symmetry, then the dual Hamiltonian is also short-range interacting and also has Z2 cross Z2 symmetry. Then you can distinguish in the dual Hamiltonian trivial state with spontaneously symmetry broken state. And the spontaneous symmetry broken state in the dual Hamiltonian is mapped back to the, it is distinct from the trivial state. Then in terms of original Hamiltonian, it corresponds to SPT because it's always distinct from the trivial state. So actually, technically, there was nothing, prevented us from finding the SPT phase back in 1992, but somehow we didn't ask this very simple question for 70 years, so we only realized this in 2009. Okay, but also, I mentioned that back in 92, I found that this Z2 cross Z2 hidden symmetry is broken only when spin quantum number is odd, but it's not broken when spin quantum number is even integer. And as I mentioned, I didn't understand what it means, but now it's with those heuristic arguments, it's kind of easy to see the difference between even and odd, because for example, this time reversal argument, we consider H state. So even spin, so for any integer spin, AKT state, we have H state. But this H state has spin S half for spin S AKT state. And if your spin quantum number S is odd, then H spin has half odd integer spin. Then the degeneracy is protected by Cramer theorem. But if you have even spin quantum number in bulk, then the edge state has S half, which is still integer. Then there is no protection from Cramer's theorem. So even though the AKLT state has some edge state, it is not protected by something fundamental like a Cramer's theorem, which means that you can somehow kill this edge state while keeping the symmetry. So that means that the even spin AKLT state, or more generally, even spin Holden gap phase is actually trivial, not really SPT. And so my tiny result back in 92 kind of captured this difference, but at that time, I didn't know, and we didn't know what it means. But after 2009, it was kind of clear.
Does this mean that there's no gapless point in the interpolating?
I'm coming to that point.
Okay.
Thank you for that question.
Thank you.
So indeed, after our paper in this 2009, several people tried to verify this numerically, and I'm showing one particular paper by Professor Tonegawa and collaborators. So they study this Hamiltonian for spin 2. So this is the regular XXZ chain plus this same uniaxial anisotropy SZ square. But this is for spin 2. Okay. Then in this delta D two parameter phase diagram, they studied ground state phase diagram, and this is it. So first, when you crank up D to large value, then again you have a trivial large G state, which is basically the product of S equals 0, really trivial state. But if you set delta equals to 1 and the D equals 0, this is a regular Heisenberg chain, but for spin 2. And in fact, it's actually gapped phase, but this gapped phase becomes very, very narrow in case of spin 2 and higher. That is, if you slightly decrease delta from anisotropy parameter delta from 1, then you easily enter this X5 phase, which is critical, gapless. And if you slightly increase delta, then you enter the long-range magnetic order phase, Nail phase, which is conventionally ordered phase. But there is still a finite window of gapped phase, which corresponds to Holden gap. So for higher spin, the Holden gap phase shrinks, but it's still finite. And then what they found in this numerical phase diagram is that there is a narrow belt of continuation of Holden gap phase, but it's actually connected to this trivial large D phase without any phase transition. So this shows that spin 2 Holden gap phase is actually essentially trivial. And also funny observation is that so between this large D and this Holden, there is a narrow strip, which is actually SPT, because this phase, which we call intermediate, is actually non-trivial SPT, because this corresponds to this type of AKUT, variation of AKUT state. That is, for spin 2, you need to symmetrize 4 spin 1/2. Then you can create a spin 2. But you can choose 2 of spin 1/2 to be just up spin and down spin. Then they kill SZ component with each other. So as a result, this is a legitimate quantum state for spin 2 chain, but it's very essentially similar to spin 1 AKT state. So this is SPT, and this kind of phase can appear in between these two, and actually in very narrow region here, according to this paper. But the point is that this doesn't extend indefinitely, so there is an end. So you can avoid this intermediate D phase to go between trivial large D phase and the Holden gap phase. So the Holden gap phase for spin 2 is trivial, but there is also non-trivial SPT phase in the phase diagram. Okay, so yeah, I'm running out of time, but let me quickly mention that more recent development. because so far I was discussing mostly very old stuff, what was known in 1990s and what we found in 2009. But the point is that in 2009, concept of SPT phases was established. And since then, there has been a lot of theoretical studies, especially from field theory side. There is some more abstract topological quantum field theory type understanding of SPT phase. So we know a lot more about SPT than we did in 2009. On the other hand, this Kennedy-Tasaki duality, which was invented by Kennedy and Tasaki-san back in 92, is very interesting mapping. So what we could do, we can do now, actually, which we did a few years ago, is to revisit this Kennedy-Tasaki duality transformation with a modern viewpoint. Then we can extend this mapping as well. And actually, this was mostly done by, I'm very briefly introducing two our relatively recent papers, which was mostly done by Ding Hao, who was my PhD student, now postdoc in Ghent, and Yun Chin Jen was a postdoc jointly between ISSP, my group, and Kavli IPMU. And now he's a faculty at Kavli Institute for Theoretical Science in Beijing. Anyway, so one funny point is that so as I mentioned that back in 90s, we believed that this Kennedy-Tasaki transformation can be only defined on open boundary condition. But actually, it was not quite right. I learned this basically from Ding Hao and Yun Chin. And there is a simple explanation. So as I said, okay, so this transformation requires some ordering. But even if you have a link with a periodic boundary condition, you can still pick arbitrary site as a site 1. Then you can put the number 1, 2, 3 until 0. But then the problem is that the site 0 and the site 1 is now nearest neighbors. So if you transform, for example, SZ at site L plus 1 by Kennedy-Tasaki transformation, then this SZ operator acquires a string, which wraps entire system, which is non-local. And then it appears that you cannot get rid of this string wrapping the entire system. Then this point of Kennedy-Tasaki transformation is lost. Well, that was what I thought back in 1990. But actually, if you are familiar with the Jordan-Wigner transformation between fermions and the spin-1/2 hardcore bosons, then we have very similar stuff. So if you map fermion to hardcore boson, you get a string. But still, people apply Jordan-Wigner to periodic boundary condition. And actually, I did many times. And the point is that this string, which covers entire system, if you look at this carefully, then actually this is nothing but one of the symmetry generator of the global Z2 cross Z2 symmetry. Actually, so this operator is nothing but a global pi rotation about Z-axis. So it's one of the symmetry generator. And we are interested in Hamiltonian with this Z2 cross Z2 symmetry, which means that your eigenstates are all eigen state of this symmetry generator. So you can replace this non-local string with a symmetry eigenvalue. So you actually do the same for Jordan-Wigner. And if you do that, you can replace this string with just a number. Then you can still obtain short-range interaction Hamiltonian and so on. And then the complication is that the boundary condition in the dual system may be modified from the original system. That is, if you impose a periodic boundary condition in the original system, depending on the symmetry charge, the dual system may obey the anti-periodic or twisted boundary condition. But if you keep track of the boundary condition correctly, then this still works on the link. And then there are two interpretations. So one interpretation is that you can regard this boundary condition whether periodic or twisted or periodic or anti-periodic as an extra degree of freedom. Then in that view, actually you map from one sector to another sector by this Kennedy-Tasaki transformation. So the Kennedy-Tasaki transformation is still unitary in the extended Hilbert space, including this extra degree of freedom. But there is another viewpoint that is you want to fix the boundary condition in the original system and the dual system. Then, depending on the symmetry charge, if you apply the Kennedy-Tasaki, then you may obtain a consistent boundary condition to what you impose, or you get a different boundary condition from what you impose. Then you can say that if you obtain a different boundary condition, then it doesn't match my boundary condition. So then state must vanish, quantum state must vanish. So if you regard this transformation in this way, then some states vanish under Kennedy-Tasaki transformation. So this transformation is no longer invertible or unitary. So actually, this is an example of so-called non-invertible symmetry transformation, which is somehow hot topics these days in field theory people. So in this way, you can connect the Kennedy-Tasaki transformation to the modern concept of symmetry, non-invertible symmetry. And also, okay, I'm running out of time, so I skip the detail. But so now, as I mentioned, there is a more abstract understanding of the SPT phase and relation between the trivial phase and SPT phase. And based on this topological quantum field theory kind of understanding, we can construct a Kennedy-Tasaki transformation in abstract way. And this abstract transformation can be implemented back on the lattice if we consider the system of spin 1/2 consisting of sigma spins and tau spins. And one of Z2 is a spin flip of sigma spins, and the other Z2 is a spin flip of tau spins. Then we have Z2 cross Z2 symmetry. And we can actually, Lin Hao and Yun Jin implemented this topological quantum field theory type operation back on this spin 1/2 system. And we have this explicit expression. And by combining these two expressions, we can write down the Kennedy-Tasaki transformation for this spin 1/2 system. Then, for example, we can start from this very trivial system. This is just a classical Ising chain for sigma spins and tau spins. And sigma and tau are completely decoupled in this Hamiltonian. Each of spin, sigma and tau, just have a classical ferromagnetic Ising model. Then the ground state is obvious, just a ferromagnetic state in sigma and a ferromagnetic state in tau. But we can apply this, and I have to say that, of course, a ground state breaks this Z2 cross Z2 symmetry spontaneously because it's just a ferromagnetic system. But now we can apply this Kennedy-Tasaki transformation to this very trivial Hamiltonian. Then this Kennedy-Tasaki mapping actually couples sigma with tau, and we end up with this Hamiltonian. So sigma z tau x sigma z and tau z sigma x tau z. So this is more non-trivial model, but actually this is a well-known model called a 1D cluster model, which is known to have Z2 cross Z2 SPT ground state. So the result is known, but using this Kennedy-Tasaki mapping, we can relate a very trivial spontaneous symmetry breaking phase with Z2 cross Z2 SPT phase. So in this way, we can reproduce a known result of the cluster model. And we can start from more complicated ground state, but with a known ground state. So I skip the detail, but we can start from various well-known kind of ground state, often with decoupled sigma spins and tau spins, then apply this Kennedy-Tasaki transformation. Then we can find a family of different kind of SPT phases. So this is more recent application of this very old Kennedy-Tasaki mapping invented in 92, some generalization. So, and those are our works, but now this Kennedy-Tasaki transformation became a very popular subject in this SPT phase and quantum field theory business. And there are many, many papers appearing recently, which I admit that I'm not really following completely. So yeah, to conclude, yeah, SPT phase is distinct from trivial phase only in the presence of symmetries. And many of the features were recognized back in 1980s to 1990s for Horden gap phase, but somehow we missed asking the crucial question, so we didn't have this concept of SPT phase until 2009. But this Kennedy-Tasaki duality mapping constructed in 1992 relating SPT to ISSP phases is now one of the hot subjects these days because this is a good example of resurgence in so-called generalized lambda paradigm, because topological phases became so popular, and people were saying that topological phases are interesting because it goes beyond lambda paradigm. Lambda paradigm means that you can classify all the phases by patterns of spontaneous symmetry breaking. But in topological phases, there is no spontaneous symmetry breaking. So it's outside lambda paradigm. So then this is interesting. That's was a huge argument. But one trend recently is that you can generalize the concept of symmetry. Then you can still explain at least some of the topological phases in terms of spontaneous symmetry breaking. And this Kennedy-Tasaki duality mapping is actually one of the very early examples of such a concept, I think. So thank you for your attention.
Yeah, thank you very much, Oshikawa-san, for very
Sorry
great
for
talk.
going over the time.
But your personal experience is very stimulating for young scientists, and as well as recent developments. Yeah. So now Oshikawa-san's talk is open. So if you have a question, please raise your hand button. Yeah. Harada-san, could you ask your question?
Hi, hi Masaki. Thanks. Very nice talk. I really enjoyed it. I wanted to ask you about, and maybe Tasaki-san is also around, about this. What this Kennedy-Tasaki transformation and the insights generated from it mean in terms of the other representations in which we view the Hilbert space of spins. For example, you talked about the Jordan-Wigner transformation towards the end, and I wanted to understand whether the Jordan-Wigner transformation gives some insight into these dualities. In particular, for example, if I think of spin 1 objects as in terms of fermion pairs, then is there some way in which the string operator can be absorbed into one of the Jordan-Wigner strings, and can we get some intuition from it?
Yeah, thank you. So you're asking the relation between this Kennedy-Tasaki and Jordan-Wigner or something like that? So your question is the relation between Jordan-Wigner and Kennedy-Tasaki transformation?
Broadly, my question is, if we think of the Kennedy-Tasaki transformation in the language in which the spin 1 objects are mapped into fermion pairs, which are triplet, how does the Kennedy-Tasaki transformation look like? What is the what do these symmetry broken states represent, and can we get some new intuition, and has this been explored broadly?
Yeah, okay, thank you. Yeah, that's an interesting question, but okay. Short answer is I don't know. So I just noticed some similarity between two transformations, but they are obviously very different. But on the other hand, okay, so I recently attended a talk by Xie Chen of Caltech, and she has some formulation, some sandwich formulation or something. So you sandwich some higher dimensional phase with from two sides and so on and so on. Then she argued that you can understand the Jordan Wigner and the Kennedy Tasaki in a unified way or something like that. So maybe we should look into the details of this CHN argument. Honestly, I didn't really digest her argument, but she was at least trying to formulate Jordan Wigner and Kennedy Tasaki in a unified formulation. Yeah. But I don't know much beyond that.
I see. Thanks. Very nice.
Thank you. Yeah.
Thank you.
Okay, then next question. Nishimura-san, could you ask your question?
Thank you. So I would like to ask you about the Z2-Z2 symmetry. So after Kennedy-Tasaki transformation, this symmetry becomes manifest. But of course, you can go back to the original model, and the model still has Z2-Z2 symmetry in a very hidden way. So can you just define the order parameter of this Z2-Z2 symmetry in the original model? And why is not that is impossible?
Okay, so actually the issue is kind of subtle. So actually the original Hamiltonian also has Z2 cross Z2 symmetry, and the dual Hamiltonian has also Z2 cross Z2 symmetry. And in fact, I didn't realize this point back in 1990s, but actually the symmetry generator of this global Z2 cross Z2 symmetry is exactly the same between the original system and the dual system. So in that sense, it's not quite correct to say this symmetry of the dual Hamiltonian as a hidden symmetry, perhaps. But still, I think the symmetry breaking is hidden in the original system. So the thing is that in the dual Hamiltonian, we discuss spontaneous breaking of the Z2 cross Z2 symmetry, which means that in the dual system, all the spins are polarized to certain direction. So that's a usual spontaneous symmetry breaking.
Right.
But if you transform this ferromagnetic state in dual system back to the original system, then you still break the symmetry, but the symmetry is broken only at the edge. So you are polarizing edge spin to certain direction. That's how this symmetry is broken in the original system. But the polarization of edge state is not spontaneous symmetry breaking in a macroscopic sense. So this polarization of edge doesn't mean spontaneous symmetry breaking in stat-mech or thermodynamic sense. That's a difference. But actually, the symmetry is the same. So that's a kind of very subtle point.
So the bottom line is that you cannot really define a reasonable order parameter in the original.
Well, that's a string order parameter. If you
that's
ask.
the string order parameter.
Yeah, because I try to explain, but where is this? Yeah, this. So in the dual system, you can detect the SSB by this usual spin-spin correlation function. So if you have SSB, this you must have this long range order. You can detect by spin-spin correlation function. That's a completely standard business.
Yes.
But then you can go back to the original system. Then this spin-spin correlation function is exactly mapped to this DSC with a string in between.
Okay. Yeah.
So when the spontaneous symmetry breaking happens in a dual system, then you must have a long-range string order in the original system.
Right.
So that is the meaning of the string order parameter. Although Denise and Rommels introduced this string order parameter heuristically, without this kind of understanding. But it turns out that their string order parameter exactly detects the spontaneous symmetry breaking in the dual system.
Okay, so this is just a standard order parameter. If
Yeah,
you
in the
go
dual
to
system.
both system. Okay, thank you very much.
Yeah.
Thank you.
Thank you for the question. Yeah.
Okay, the next question, Chiba-san, you just, yeah.
Thank you very much for your nice talk. And if I understand correctly, the in the Kennedy-Tasaki transformation, the locality of the operator is not always kept.
Right.
Okay. Then my question is that is there any example that integrable systems and non-integrable systems are connected by Kennedy-Tasaki transformation? I asked this question.
Yeah, thank you. That's very interesting question, but I don't have immediate answer. But in this room, I have Katsura-san. Maybe he knows better. So do you know the mapping between, let's say, spin-one integral system? Okay, so well, we know spin-one integral chain like some what's the name? Wimin Sutherland or something like that. Yeah, Babujan, Taksujan, Hamiltonian. Then we can certainly apply Kennedy-Tasaki mapping to, let's say, Taksujan, Babujan model. Then we should get some complicated model. But can we say something about these models?
Just the BLBQ class of models,
okay.
right?
But
you have a biquadratic chart.
Yeah, but usually we get this string E exponential I pi SZ or something in between these spins. So probably it becomes more complicated.
But because the Kennedy-Tasaki transformation is just unitary transformation.
Yeah.
I mean the mapped model.
Yeah.
Okay.
Yeah.
Right?
So I guess I'm not sure how really useful this is, but we can say that I have this strange looking model which doesn't look like an integrable or anything, but I can map this strange model to well-known integrable model like a Taktajan-Babujan model by Kennedy-Tasaki. Then this strange model is also kind of integrable. We know exact thermodynamics and so yeah, I think there is an application like that. Although I'm not sure how physically interesting it is, but we can make some statement on some strange model which can be related to the non-integral model via Kennedy-Tasaki transformation. Yeah, thank you.
Thank you very much.
Okay. So is there any other questions?
So there's a question in our room. So can you give us
okay. So I cannot see.
1 minute? Yeah.
So I have a few questions. So in this setting, you considered one-dimensional chain with inversion symmetry, right? So can you generalize to more symmetry other than inversion symmetry? For example, like crystalline symmetry in higher dimensional systems.
Okay, yeah. So yeah, one thing is that so in 1D there is not so much variation, I guess, but this Holden gap typeface Z2 cross Z2 SPT can be protected by one of those symmetries, time reversal or bond-centered spatial inversion or this global Z2 cross Z2. But yeah, of course, if you go to higher dimension, there are more symmetry, crystalline symmetry, and so on. And also by now we know many examples of SPT phases in higher dimensions. But then one interesting question is whether we can generalize this Kennedy-Tasaki duality mapping to higher dimensions. And what I know is that at least for some higher dimensional system with subsystem symmetry, we can generalize. I know such examples. And I think, yeah, people are working on in that direction. So maybe there are Kennedy-Tasaki transformation for more general 2D, 3D system. But what I know is a system with subsystem symmetry or some kind of gauge symmetry. For that, I know explicit examples. But in general, I don't know. Yeah. And also, I have to say that so this Kennedy-Tasaki mapping is only applicable to this Z2 cross Z2 global symmetry. And if you only have time reversal or spatial inversion symmetry, I don't know similar duality mapping. Yeah. I also don't have a proof that such duality mapping doesn't exist just for time reversal, but I try to find, but to me, it looks like difficult or so maybe duality doesn't exist for time reversal, but I'm not totally sure.
Okay, so and the second question is that so you consider the case where coupling constants are spatially uniform, right? So can you generalize it to random coupling with keeping inversion symmetry?
Yeah. So actually, in some of my paper with Fujikun, we did discuss this kind of stuff. So even if the coupling is non-uniform, as long as you keep the spatial inversion, we can apply the same. Although I have to say that such a restriction is kind of artificial because you can have strong bond, weak bond, some random coupling, but it should appear in exactly the same pattern in the other side to maintain the spatial inversion. But as long as you maintain the spatial inversion, this still works.
Okay, thank you.
Oh, but here's a remark. But if you have time reversal on global Z2 cross Z2, then translation invariance doesn't matter. So, of course, this is not about the duality transformation, but for like characterizing PT phase by index, then you don't need any translation invariance. And and actually, you do need for your index, but Yoshiko Gata's index doesn't care about translation invariance. Yeah.
So now the theory is more advanced.
Yes.
Thank you. Yeah. Thank you.
Okay, is there any other question?
Yeah, there's another question from our
okay.
our room.
Thank you for that nice talk. So there are other types of non-local transformation in the field of topological phases, like flux attachment in fractional quantum Hall states, which maps the fractional quantum Hall states to some kinds of Bose-Einstein condensates. So do you have any comments on such other types of non-local transformation from a modern viewpoint?
Yeah, thank you. Yeah, actually, I have been fascinated with this flux attachment kind of transformation, but I have to say that it's much more subtle than this Kennedy-Tasaki or Jordan-Wigner, because at least Kennedy-Tasaki and Jordan-Wigner, I can define completely, make it well defined on the lattice system. But the flux attachment, as far as, maybe in some cases, but at least in the original kind of application, it's, more like a hand waving type argument. But in the past, I tried to support this flux attachment kind of argument by deriving some result from flux attachment picture, which is not rigorous at all. But then confirming such, consequences or prediction from flux attachment argument by some direct numerical calculation or something. And often it seems to work. So that suggests that flux attachment idea is not completely meaningless, but still I found it difficult to formulate it in rigorously not in Tasaki-san's standard, but in my standard, even in my standard, making it rigorous looked like difficult to me. So Okay, so my very short answer is no, but I do think flux attachment does work, at least in some cases. So yeah, it's also interesting question to, put the flux attachment kind of transformation to more rigorous setting. But I don't know the clear answer at this point.
I see. Thank you very much.
So it has a question from the student room. So if no, may I ask a question? Maybe my question is related to the Tasaki-san's talk. So by hearing Oshikawa-san's talk, I have a naive question. So if we apply the Kennedy-Tasaki transformation to the, for example, twist operator based index, topological index appeared in the Tasaki-san's talk, probably everything can be written into the language of the spontaneous symmetry breaking. So is it, I'm not sure, but does it simplify the proof process of the holding gap or quantum phase transition between the Holden state and large D state? Do you have any comment on such a application of Kennedy-Tasaki transformation to the twist operator in the Tasaki-san's talk?
Oh, so you're asking, so the twist operator is twist operator, but we can also apply Kennedy-Tasaki to the twist operator. Actually, I don't know what happens. So one problem is that maybe Tasaki-san didn't mention explicitly, but this SPT is supposed to be protected by only discrete Z2 cross Z2. But when we use twist operator, we also need a U1, somewhat bigger symmetry, right? So perhaps this Tasaki-san's twist operator argument only works when the spin chain has an extra U1 in addition to Z2 cross Z2. Am I right? Perhaps Tasaki-san can comment.
Yeah, I think so. I mean, I agree that it doesn't work as it is. And well, physically speaking, I think twist after this duality transformation is not doing something right. So yeah.
But the Kennedy-Tasaki is just a unitary, so that it doesn't change physics.
Oh, but but you mean twist means different thing for
of course, yes.
Yeah, of course, something should be preserved, but this twist operator is utilizing this U1 symmetry. So if you lose U1 symmetry, then
yes.
Okay, maybe this perhaps this U1 is hidden in some way, but it becomes difficult to identify. So maybe it becomes difficult to go beyond. Of course, you can apply, but you can apply Kennedy-Tasaki to twist operator, but then you get some strange operator, and it's not easy to figure out what to do with that. But, maybe there is some way forward, but not easy to figure out.
Yeah, but to be honest, I haven't thought about that. So, I mean,
maybe there is some.
As I didn't say explicitly, but I always want to get rid of U1 symmetry. And so in order to do this twist game like I did, we need U1. But but physics doesn't require U1. So that's something that it's bothering me all the time. So yeah, I will think about that. Thank you.
Okay, well, this is just my naive question. So is there any other questions?
Actually, can I ask a question to Tasaki-san?
Okay.
So that is very non-scientific. So I pointed out that your talk title has original reference 35 years ago. My question is that is there further original reference? I mean, 元ネタ of your lecture title in 1990,
Ah,
or you just so this is cool title.
all that. I think it comes from something about constructed field theory or axiomatic field theory, some mathematical physics thing. Doesn't anybody know about this? Something. Yeah, I don't know, like Whiteman or whatever.
I see. Okay, maybe.
Yeah, something.
Is it PCT, spin statistics, and all that?
Oh,
I
yes.
see.
Oh, yes. Oh, yes. Who is
Yeah,
that?
now-
Who is
now
this
I kind of-
educated person? Good.
Okay.
Yeah.
Okay. So there is a further original difference to this. subtitle. Yeah. Thank you.
Great.
Okay, any other question? If not, let's thank Tasaki-san and Oshikawa-san again. Yeah, thank you very much.
Yeah. Thank you very much.